Thank you, everybody. Thank you, Michael, for the kind words, and thank you all for your kind reception. I've never visited Namibia before, and this is my third day in the country. I'm enjoying it immensely so far, and I'm very, very grateful for the great welcome I've had so far. I'll show you a little bit later on in the talk some of the adventures that I've managed to have already so far, and I hope, and I sincerely believe it's the beginning of a long collaboration, not just between myself and the project, but between Oxford University and UNAM and the whole of astronomy in Namibia. So in this talk, I'm going to spend I'm going to break the talk into approximately 3 parts. I'm going to spend the first third of the talk telling you a little bit about what black holes are. Now, many of you may have read a lot or some literature about black holes, and perhaps some of what I'm going to say next appears to be relatively straightforward. But what I find is that, they're such remarkable objects. It's really worthwhile, periodically to just step back and realize what it is that we're observing. We're observing objects which are as simple as subatomic particles, which are definitely out there in space, and yet which are the size of entire solar systems. They're really remarkable, unlike anything else in the universe. So I will tell you a little bit about what black holes are for the first third of the talk. For the second third of the talk, I'm going to tell you a little bit about the work that I've been doing for the last 15 years or so, working with radio astronomers and a big new radio telescope in South Africa. I've been associated with this project for a long time now, associated through the South African Radio Astronomical Observatory and through the University of Cape Town. It's delivered some extraordinary results, and I've been very, very fortunate to be part of that program. And then finally, the final third of the talk is the bit that you'll all be waiting for, which is the discussion and so of this new project in Namibia. We're building this thing called the Africa Millimetre Telescope, which is really going to transform, very, very sincerely, it's going to transform some of our understanding of black holes in astrophysics. So let me start off then. What are black holes? As I say, they are. It's really important to try and understand what they are. And it's very, very important to always remind yourself that they are like nothing else that we observe in the entire universe. So I'm going to start with this quote by Kip Thorne. Kip Thorne will be known to many of you. He's famous for many, many reasons. He won the Nobel Prize Physics in 2017 for his work in developing over a long period of time the first detector of gravitational waves. Gravitational waves were long predicted and were detected for the first time when 2 black holes merged and were picked up in 2015. And very, very rapidly thereafter, him and 2 other pioneers of the field were awarded the Nobel Prize in Physics. He's done many, many things. I recommend reading some of his early popular science books. They're absolutely extraordinary until a time of the 60s and 70s in the US, where it very much felt like the new physics which was happening was a bit like the Wild West. He also is the guy who basically was the graphics consultant for the film Interstellar. So some of you may have seen the film Interstellar, where there is a giant black hole. This is the guy who made sure that they were actually doing an accurate representation of black holes. So anyway, by now you all have read this, but he says, why are black holes so different from all other objects in the macroscopic universe? So macroscopic just means everything above the quantum scale, so everything on any kind of reasonable scale. Why are they and they alone so elegantly simple? If I knew the answer, it would probably tell me something very deep about the nature of physical laws, but I don't know. So I'm going to try and explain to you just in the next 10 or 15 minutes why, what black holes are and why they really are fundamentally different to all other things in the universe, and why that makes them extremely exciting to study. So first off then, what is a black hole? So imagine that the slide which you're seeing here, all that black stuff is space. A black hole is essentially a region in space. Okay, so black holes exist. I should emphasize this. We have overwhelming evidence, even before we had these images of black holes, that they exist out there in space. And we can measure their size, more or less. And we know that nearly all of that space is completely empty space. So the first thing you should realize is that black holes have no surface, and they're almost entirely empty space. So they're mostly empty space from within which nothing, even information, can escape. And this means that, as you'll see in a moment, that not even light, because light, of course, can carry information, not even light can escape from within a black hole. And this is from where, of course, the name comes. So how do you make a black hole? So there's only one thing you need to do to make a black hole. You can make anything into a black hole. You take some mass and you squeeze it. Beyond a certain density, any object will become a black hole. Actually, a few years ago, I was giving a public lecture and my daughters came along to the lecture, and the younger one said to me afterwards, she said, so Daddy, does that mean, I could become a black hole if someone squeezed me small enough? And to which her elder sister replied, yes, should we give that a try? So beyond a certain density, anything can be made to form a black hole. And an important point to make here is that in the present day universe, we know of only one process that can naturally make black holes, and that's the deaths of massive stars, which can sometimes result in the production of a black hole. So how would we make the Earth into a black hole? So if we took the Earth and we squeezed the Earth to about 2 centimeters across, it would form a black hole. Okay, so this is the radius to which you would have to squeeze the Earth. If you took the Earth, you squeezed it to 2 centimeters across, the Earth wouldn't stop at 2 centimeters. At this point, there would be no known physical forces which could stop it collapsing to a point. So all of the mass that until you had squeezed it was constituted the Earth would now collapse down to a single point. And some of you will already realize there's a problem here with physics. You can't have a very large amount of mass at an infinitesimally small point. And this really why we don't have a very good description of the centers of black holes, and there must be some new physics lurking there. So outside of a black hole, the escape velocity is less than the speed of light. So what do I mean by that? What I mean by that is if you're not inside a black hole and you have a spaceship that can travel fast enough, but of course nothing can travel faster than the speed of light, but as long as it can travel fast enough, then it can get to anywhere else in this bit of the universe. So a spaceship here could drive around to a point here. Inside a black hole, the escape velocity, because the density of the matter is so great, is greater than the speed of light. This means that once you are inside this region, no matter how powerful the engines on your rocket, no matter how fast it can go, you can never leave this region. And in fact, there is an additional feature here. If general relativity, which is our current best description of the universe, is correct, then once you cross this point, you must inexorably travel towards the center. You can't hang around here. You just have to go towards the center. And the boundary between these two bits of space, normal space and the inside of the black hole, which again, to emphasize, is nearly all empty space, is what we call the event horizon. So nothing, we cannot see anything once it crosses the event horizon. If something that was previously in our part of the universe crosses the event horizon, it's lost to us forever. Not only can it not come back, but we can never see it again. It can never send a signal to us. So at the center of the black hole, as I said, all the mass that crosses the event horizon must inexorably end up at the center. So at the center of the black hole is a point which we call the singularity. And everything which crosses the event horizon ends up here. There is a small technical exception to this in the case of a rapidly rotating black hole, but let's not worry about this here. This means that you have extraordinarily high densities at this point. It's also interesting to note that, if Big Bang cosmology is correct, then about 14 billion years ago, our entire universe began in an equivalent singularity, a gravitational mathematical singularity. Now, I want to emphasize another point about black holes, which makes them fundamentally different to everything else. So the number of pieces of information, the number of things you would need to write down to fully describe any everyday object is extraordinarily large. So there's a number here, which is 6 followed by 23 zeros. This is Avogadro's number. It's been known for a very, very long time. And it's very approximately to within a factor of a few, the number of pieces of information you would need to record in order to fully describe 1 gram of ordinary matter. So here's a piece of ordinary matter. This is my dog with one of his beloved tennis balls. And everyone is familiar with this concept that in order to fully describe him or the tennis ball or anything else or any of you, you would need a very, very, very large number of numbers written down to fully describe it. A black hole, on the other hand, a classical general relativistic black hole, which is how we describe them in our observations and modeling of the universe, is entirely described by just 3 numbers. Its mass, its spin, and its charge. Now, you may be thinking at this point, but there's going to be some trick here, right? That these are going to be somehow really complicated numbers. It's not going to be as simple as that. But no, it's not. It really is as simple as that. There is an archetypal black hole called Cygnus X1. Some of you may know that there was a famous bet between Kip Thorne, who I mentioned earlier, and Stephen Hawking, And Stephen Hawking finally conceded the bet that black holes did exist based upon evidence of observations of a black hole with the great name Cygnus X1. But the point about Cygnus X1 is that it has these three numbers. The mass is 12. The units in this case are solar masses. So this means that that particular black hole weighs 12 times as much as the sun. Its spin is 0.9. We measure the spin of black holes on a range from 0 to 1. That's it. If their spin is 1, they're rotating as fast as possible. And if their spin is 0, they're not rotating at all. And we think the spin of Cygnus X1 is about 0.9. That's pretty rapidly rotating. And the charge is 0. And again, this is one of the things about black holes. Not only are they entirely described by three numbers, but as far as we can tell, all of the black holes that we observe in the universe have a charge of 0. So in fact, there's only two numbers, and that's it. And again, bear in mind that the most massive black holes which we can observe are as large as entire solar systems, and yet they can be entirely described by just two numbers. This makes them fundamentally different to everything else in the universe. So the event horizon is the boundary of the black hole. Normal matter falls in. Normal matter is described by all of these enormous numbers of numbers. You need all of this detail to understand what's going in. It crosses the event horizon, and all of this information seems to be lost. All of the mass ends up at the singularity or very, very close to the singularity, which means that forces go more or less to infinity as distances go to 0. Densities go to infinitely large as distances go to 0. And essentially, it cannot work. General relativity cannot work at the center of black holes. So the event horizon, which we observe, and I'll show you more observational results, some of which are well known to you shortly. General relativity tells you that if something collapses, it produces this event horizon around it. It also tells us that at the center, it's not a full description of physics. There must be something else going on, because you cannot have distances going to 0, forces and mass densities going to infinity. And yet it's hidden from us by the event horizon that the collapse itself caused. So new physics is required in order to understand fully black holes. Okay, so one of the most iconic pictures in astrophysics in the last decade or so came out in 2019 when this image was produced by the Event Horizon Telescope collaboration. And I'll tell you now that the Africa Millimetre Telescope project, in which Namibia is going to host, is a project to join in to the Event Horizon Telescope. So Namibia will soon be a fundamental partner in this project. But this was the first image that was released in 2019. And although we had a lot of observational evidence for many decades that black holes exist, and I refer you back to Stephen Hawking conceding a bet to Kip Thorne, this is really the killer. This is the one that actually allowed us to directly see a black hole. This is a massive black hole at the center of a galaxy called M87. The star indicates that it's the black hole at the center. We see a bright ring of emission in a millimeter image. This is a sort of radio astronomy image, and there's a black hole in the center. There literally is a black hole in the center of the image. It's a little bit bigger than the actual event horizon itself, but when you look here, you are looking directly into the event horizon of the black hole in M87. And I think there could be no better, more obvious in-your-face proof that black holes existed than this image. There is another very interesting phenomenon associated with black holes, which is going to pop up a few times in this talk, so I'll mention it now, which is that they produce something called relativistic jets, which move away from them. Now, if you take a simple description of a black hole, you say you have an object with very strong gravity, what do you think will happen if you let matter flow towards it? Then all the simulations and back of the envelope maths will tell you that matter will fall down to it and will fall into it. If it has a bit of what we call angular momentum, it will rotate faster, but it will still fall into it. All the stuff will fall into it. But that's not what we see with black holes. What we see with black holes is that there's this phenomena of jets that move away from the black hole. So what I'm showing you here is an optical image of some galaxies, and in the center of this galaxy here is a supermassive black hole, just like the one in M87. When we take, so this is an optical image, the same wavelengths that you see with your eyes. When we take a radio image, this is what we see from this galaxy. We see these extraordinary jets that are far larger than the galaxy itself, extending very, very large distances, terminating at very large distances and producing these big plumes or lobes of radio emission. I'll show you some examples later, but we already know in this case that if you track over time components in these jets, then you see very clearly that it's moving outwards. And when you zoom in at higher and higher resolution, you see that these enormous structures here track all the way down to just above the event horizon of the black hole. Now, I can tell you, we don't really know how this phenomenon occurs, but it must occur in a torus of rapidly rotating magnetized material very close to the black hole. So a general description of what we think is happening in these black holes is that matter falls down towards them. As I say, because it has angular momentum, because it's rotating, it rotates faster and faster as it falls down, just like water going down a plug hole. This matter crosses the event horizon, but somehow magnetic fields and generated energy is released, and matter also flies away from the black hole. So this was the first Event Horizon Telescope image of the supermassive black hole in the giant galaxy M87, which came out in 2019. In 2022, the Event Horizon Telescope collaboration released a second image of the black hole at the center of our galaxy. And this is a black hole called Sagittarius A star. And then there is a third scale of black holes, which are called stellar mass black holes. And I'll return to those in a moment. Let's look first at the comparison of the scales of M87 and Sagittarius A star. And M87, you can see that the sun is a small dot at the center. This ring here is the orbit of Neptune drawn exactly to scale onto the image. And you can see that the black hole is bigger than our entire solar system. So, of course, when I was younger, there was another planet beyond Neptune, but this has been ruled out now. So Neptune is the outer extent of our solar system, and you can see that our entire solar system would fit within M87. In contrast, if I do the same sketch for the black hole at the center of our galaxy, Sagittarius A star, then we have the sun here. We have the orbit of Mercury, which is the innermost, of course, of the planets in our solar system. And in that case, that black hole would fit just inside it. Now, you'll recall that I said that all you have to do is squeeze something to a certain size, which scales with its mass, and it becomes a black hole. Stars which explode, massive stars which explode, tend to produce these objects called stellar mass black holes there. And this is an illustration of one compared to the size of a large city. They are very, very small. These objects can be 20 kilometers across or smaller, and they're distributed throughout space. So this is a third regime of black holes, and we call them stellar mass black holes. Okay, so that's my introduction to black holes. So hopefully I've set some of the scene for black holes, and again reminded those of you, even if you had been interested in black holes for a while, that they are really fundamentally different to anything else in the universe, and they are really worth our study because new physics lies in or close to black holes. Now, for 15 years, as I mentioned at the start of the talk, I've been working with radio astronomers in South Africa to study black holes using a new radio telescope, which was finally inaugurated in 2018. And this is a facility called Meerkat. Prior to Meerkat, there was a test array called CAT7. So this stands for Karoo Array Telescope. And of course, the joke on going from CAT7 to Meerkat for a larger array won't be lost on this audience. It's been an extraordinary journey working with this telescope. And this telescope has proved, despite doubters, I must say, in some places around the world, to be one of the most phenomenal and productive radio telescopes in the world. So I will start with one of the most iconic images which has been produced by this radio telescope. This is a wide field image of the galactic center at radio wavelengths produced by the Meerkat radio telescope. So Sagittarius A star, the black hole at the center of our galaxy, which we were talking about a moment ago, is right down here. It's an unresolvable dot right down here. That's how wide field this image is. Okay, so we're looking at several degrees instead of micro arc seconds. Extraordinary structures here. We have some idea of what some of these are. Things which are more or less spherical like this, we have some idea that these are probably supernova remnants. So a massive star exploded maybe 10,000 years ago, and this is an expanding shell of gas pushing out into the surrounding dust and gas. All of these long, thin filaments are, frankly, completely or more or less completely ununderstood. No one knows what they are. It's been quite a revelation, the images of the galactic center that this telescope has been making. But I want to draw your attention, for the sake of this talk, to a rather undistinguished little point on this diagram. So over here, I've drawn a white circle, and you can see a little structure over here. And I'm going to zoom into this structure now. And now you begin to see maybe a little bit more. Of course, it's hard for the eye not to be drawn to all of this other incredible structure. But you see this thing here, and you begin to get a sense that maybe this is some small version of those jets which I showed you earlier. Maybe this is one of those structures with a black hole at the center and it's got some lobes going in each direction. Well, indeed it is. But this is not a supermassive black hole system with vast jets, which is at a vast distance and which we're seeing through the galactic plane. This is an object in the galaxy. So this is another version of that picture. This is the object here. At the center of this structure is a 10 solar mass black hole. You recall that we call these objects stellar mass black holes. And we believe, through studies of the population of massive stars in our galaxy, both now and how we believe they evolved in the past, that there are 100 million of these in our galaxy. So let me just make that point, it's a very, very important point. There are 100 million of these. They each weigh about 10 times the mass of our sun. This means there's about 1 billion solar masses of black holes in our galaxy, which completely dominates the amount of black hole mass, if you like, that's in Sagittarius A star. So most of the black hole mass, or the black hole action, if you like, going on in our galaxy is a distributed population of these kinds of objects. Most of these black holes are drifting through space. If you split them up naively through the entire volume of our galaxy, then you find that probably there should be one within about 10 to 30 light years of the Earth, which I'm sure you appreciate on a cosmic scale is very, very close indeed. Don't worry, the cross section of the chance of one actually hitting Earth is tiny, but the chance of us finding one, perhaps in the next few years or decades, and actually being able to go and explore it, this is a side story to the main story here. There's a chance there. Anyway, these objects are called X-ray binaries because they get very hot. The black holes get very hot as matter falls down towards them. We see them in X-rays. So when we observe these X-ray binaries, they are too small. Their physical size is too small to directly image them with the Event Horizon Telescope. But there are other ways of studying what happens near the event horizon in them. So this is a fairly realistic, we believe, artist's impression of what happens. Instead of it being all the gas and dust that's in the center of the galaxy falling down towards the black hole, in this case, because they have a binary star companion, they get close enough to the binary star that matter basically transfers off through gravitational attraction from the star that they're in a binary orbit with, spirals down towards the black hole, and exactly the same physical processes happen around this stellar mass black hole that happen in these supermassive black holes. They're scaled down in size, and they're scaled down in time scale as well. So they're smaller, but they also happen much more rapidly. Now, we can't image the event horizons, but by making X-ray observations, we can see what's happening very, very close to the black hole. So it just so happens that X-rays are emitted from this region just above the event horizon. Since the 60s, in fact, X-ray satellites in orbit have been detecting and measuring these signals. So there is a sort of equivalence in what we can do. But the beautiful thing is that we can see the jets from these objects moving on humanly accessible timescales. So I show here an image of a stellar mass black hole with jets coming from it. And I show here an image of a supermassive black hole with jets coming from it. Now I'm going to show a movie when I press the button of the jets from the stellar mass black hole, where a sequence of images taken on consecutive days. So these images are just days apart. The right image is not going to switch to a movie, but I can tell you now, if I switched it to a movie with images taken days apart, you wouldn't see anything move at all. It's too big, too old, and too slowly evolving. These things are essentially frozen in time from our point of view. So this is what you see when you observe the jets from these stellar mass black holes. You can see them moving, just taking 2 images a day apart. And when you get sequences of images, you can see just so beautifully how the emission is moving away from the source. So it's completely unambiguous here. I'm sure you'll agree that the stuff is moving away from the center where we believe the black hole is. And those of you with eagle eyes may also notice that the angle of the jet changes in this system. There's something going on here. We don't know exactly why, but the jet angle is actually precessing on the sky. Okay, so we ran a project called Thundercat between 2018 and 2023, studying exactly these kind of sources with the Meerkat Radio Telescope. It was led by myself and my colleague Patrick Vout, who is a professor of astronomy at the University of Cape Town. The project is now continuing as XCAT project led by myself. Here's just a picture of one of the many meetings we had over the years. We've been having meetings since 2013, and it's been a fantastic collaboration. And I hope to be able to build similar and as enjoyable and productive collaborations in Namibia going forward. So if I take a lot of the data that we took from Meerkat and project it into a movie that tries to compress a lot of the results down into 5 years, then you get what follows next. This is a map of our galaxy. It's projected in such a way that the plane of our galaxy is a line across the middle of the projection. The center of our galaxy is the spot right in the center. What you're going to see is circles of changing color. Circles which are blue are black holes. Circles which are yellow are neutron stars. Now, I don't have any time to talk about neutron stars today, but they're also absolutely fascinating objects that behave in many ways like black holes. And sources which we see in red are sources for which we directly saw imaged resolved jets. But I think that in every single one of these objects, when you see variable radio emission, it means that these jets are powering away from these black holes. So here's the movie. You can see the time bar cycling here. So we started off with observations of this source called GX339-4, which was our test source. And then we began observing any source which orbiting X-ray satellites told us or hinted might be active at a given time. So all of these objects here, which are blue, are black holes within our own galaxy, which had become very bright because matter was falling down towards them, had become variable radio sources because they were producing relativistic jets, and these jets were flying away from these black holes and propagating into the interstellar medium around our galaxy. And it's been an extraordinarily productive effort, as I think you can see. Prior to this project, such observations were fairly sporadic. Sometimes people would get time on radio telescopes to observe these objects, but never was there such a systematic study. This object here, J1727, went off last year. It was the brightest object we'd ever observed with Meerkat, and is currently, right now, we are tracking in weekly observations powerful relativistic jets moving away from the central source. Let me give you a couple of highlights of the project. I want to give you an illustration of what the data are really like. So what you see here is a source called Maxi J1848. You can completely forget that. It doesn't matter. But it's a black hole in a globular cluster. So some of you will know what globular clusters are. These are more or less spherical, gravitationally bound, old star clusters. There's a black hole in the center, and what you see here is a sequence of images going for nearly 2 years. And you can see, if we go back to wait till the start of the movie, you see radio emission starts off close to the core, and the radio emission separates, moving away from the core. These are blobs, if you like, or these are plasmons, large clouds of plasma, which are part of these jets. They're moving away from the central black hole at greater than half the speed of light. And there's incredible details in here that we're still trying to pick apart. These ejecta, they decelerate as they move away from the central black hole. Sometimes they brighten, sometimes they fade, and we're not exactly sure what's happening here. They must be hitting density enhancements or clouds in the interstellar medium. Another highlight is led by my student, Kelly Bokhile Khazielawe, at the University of Cape Town, and she's made this deep image of a neutron star system. This is the only remaining mention of neutron stars, but in many ways, they behave like black holes. So what you're seeing here is there's a neutron star X-ray binary right in here, and we know that it has jets which point on this angle. We know that this sort of spherical shape around here is a supernova remnant that's about 4,600 years old. This is a very southern object, by the way. It has a declination of -57, so the northern hemisphere never observed this object. This supernova remnant has been dated to be about 4,600 years old, which makes this probably the youngest known one of these binaries in our entire galaxy. The extraordinary thing is that with our deep images from Meerkat, we knew that jets were propagating in this direction. You can now see there's this spherical hole on the edge of the supernova remnant, and the jet has punched a hole in the edge of the supernova remnant and is inflating this bubble out here. This is really extraordinary. No one's ever seen this phenomenon before. And this is really telling you about the evolution of a combined sort of jet supernova remnant system as it ages in its first few thousand years. And then finally, we have a paper which we hope to submit to Nature in the next couple of weeks. Here's a sequence of images here with increasing time. These, again, are real radio images from Meerkat. The straight line down, which doesn't move. So the x-axis here, if you like, along here, this is space, and this is time. This bit here, which doesn't move, is a black hole. This thing here moving away from the black hole, and you can see decelerating because it's a curved line. This is one of these jet ejections. This is the fastest moving object ever observed in our galaxy. Some of you, perhaps in the audience, have heard of a thing called the Lorentz factor, which measures how relativistic things are. This is a Lorentz factor of at least 7. Essentially, this puts this in the ballpark with all the most relativistic or fastest moving phenomena we've ever seen anywhere in the universe. This is the fastest thing ever seen in our entire galaxy. Okay, so now I want to finally come to the Africa Millimetre Telescope, which is the reason that I'm here in Namibia, and tell you how that's going to help to transform our understanding of black holes. Okay, so the Africa Millimetre Telescope is a project which has been going for approximately a decade now, and the core drivers behind it have been the University of Namibia and Radboud University, based in Nijmegen in the Netherlands. And they've been working towards the establishment of a new millimeter telescope in Namibia. The concept of this telescope was driven by the fact that it was realized that a telescope in approximately this region of the world would dramatically increase the quality of the images that the Event Horizon Telescope collaboration could make. In 2021, my university and the University of Amsterdam joined the project. And luckily, myself, Heino Falke, probably some of you have come across Heino. He's visited Namibia many times. And Sarah Markov from the University of Amsterdam. We put in a bid to the European Research Council Synergy Grant, and we were lucky enough to get awarded a large grant, which basically provided enough money to take this project across the line. So the Africa Millimetre Telescope is now happening, and we are right now, part of my visit here right now is to actually discuss the timeline for getting the thing built and sited and operating in Namibia. It's a very, very exciting time. So this is the trip. I promised to tell you something about what I've been doing in Namibia in my 2.5 days here. When was it? Yesterday? Yesterday only, yeah. Yesterday we drove to the Gamsberg, which is one of the possible sites. Here's Windhoek and here's the Gamsberg for the telescope. I went with Zandre, Delight, and Michael, who are all, of course, in the audience. Michael was generous enough to introduce me. It was a thrilling, eye-opening, and occasionally scary trip. Just so you don't think that all we did was stay down here at ground level, I want to illustrate we really were up on the top of this mountain, which is a flat top mountain, which is one of the highest points, possibly the highest point in the whole of Namibia, and potentially a very exciting site for the telescope. So this is the Earth as viewed from Sagittarius A star, the black hole at the center of our galaxy. The AMT is here. The movie will restart in a second. When you see lines on this movie, this shows you connections between different telescopes in the world, which can contribute to an image that the Event Horizon Telescope can make. So down here, we have the South Pole Telescope. Here we have some telescopes in North and South America and in the Pacific. So the whole cycle will start again in a moment. You can see that there's a period when only the Pacific is looking at Sagittarius A star, when we can't basically make images. So here we start. The first baseline is between the South Pole and Namibia. And you can see there's a whole cluster of baselines which connect to a hypothetical millimeter telescope in Namibia. And then at some later point, you get what we call the Western Array, which is the Americas and Hawaii and the Pacific join into the array. And you can probably appreciate by looking at this movie that, you know, what you would ideally want is a very, very good distribution of these telescopes all over the world. And adding Namibia to this array, adding a telescope around here in the world really enhances what we can do with this array. And I'll show this, I'll illustrate this more clearly in a moment. The dish will look something like this. It will be a 15mm dish, and it will operate up to high frequencies as high as 350 gigahertz. That's why we call it a millimeter dish. These are millimeter wavelengths rather than just radio astronomy, regular radio astronomy. Why do we want to do this? There's lots of reasons to do this, but perhaps the headline science, in the way that EHT is good at generating headline science, is we want to see black holes rotating. We think we can measure the spin, but there's nothing like being able to see it directly. Now, if you take M87, the first one imaged, which is really, really massive black hole, the rotation time is about a month. Therefore, in order to see lots of cycles of rotation, that's really a lot of effort over many, many years. Remember, the EHT is not observing all the time. It's only sometimes they can get all the telescopes together. For the stellar mass black holes, we have no problem with timescales. The rotation time is milliseconds. It might even be too fast. But we have another fundamental problem, which is they're too small to directly image. However, the black hole at the center of our galaxy, we know we can image it. There's the image there. And the rotation time is about an hour. And you'll have seen from the movie, the animation I just showed, that for something like 2/3 of the rotation of the Earth, we can image Sagittarius A star, and that imaging quality is greatly enhanced by having a telescope in Namibia. So we can track in a relatively small set of Earth rotations a significant number of rotations of the black hole at the center of our galaxy. So here's an illustration of how much improvement the Africa Millimetre Telescope might add to the Event Horizon Telescope. Here's an idealized model. These are not data, but this is what we think the black hole might look like if we had a perfect telescope. This is what the Eastern EHT looks like now. So the Eastern EHT is basically the South Pole Telescope and a lot of telescopes in Europe which can join the array. And it's essentially the first 7 hours of the Earth's rotation before the Americas can join the project. And it's terrible. I think you'll agree. And you can't recover any physics from this. However, with simply the addition of the Africa Millimetre Telescope, suddenly you can recover the ring. That's how much difference just adding that telescope adds. And again, I want you to think about this, and you saw it in the movie, that telescope connects to all of the other telescopes that it's able to. It's not that you're adding one telescope, you're adding an additional baseline, as we call them, to every other telescope in the array. It's a huge addition to the array, just adding one telescope. So let me illustrate this again. This is an idealized model now for rotating Sagittarius A star. And this is a simulated image reconstruction for the Event Horizon Telescope using the Africa Millimetre Telescope. Now, the Event Horizon Telescope has done a pretty good, the whole project has done a pretty good job over the last 5 years or longer in taking simulations and actually, predicting fairly well what the data show. So I think we can have some faith, perhaps not absolute faith, but some faith in these simulations. So we have a rotating hotspot on Sagittarius A star, which is rotating with the rotation rate of the black hole, under some assumptions about what that is. And here are the simulations of what we would recover only if we add the Africa Millimetre Telescope to the array. You can see the fundamental difference that it adds, that it really gives you adding the telescope. So just a couple of final slides then. So the EHT, the Event Horizon Telescope project, will only take up about 20% of the time of the Africa Millimetre Telescope. And this is not because we wouldn't want it to be operating as part of the Event Horizon Telescope all the time, but it's because, you'll recall going back again to this picture of the whole globe, you have to coordinate all these different arrays, which are run and owned by different countries, different organizations. You have to coordinate them to work together. And that's a political and logistical challenge. And of course, they have other science that they want to do as well. But you can do things with the AMT on its own. And this is one of the parts of the project that we in Oxford are also very, very excited about. So we're going to chase astrophysical transients. If you look up at the night sky in optical, X-ray, radio, any wavelength you like, and you wait long enough, you see things which are very, very highly variable. Now, the X-ray binaries I showed you in the movie from Meerkat earlier are just one example of this, but there are so many different phenomena out there. And these are usually signposts of some of the most exciting and important to astrophysics that's out there. So here's just an example. You're all familiar with the case of supernovae out there in the sky, where a massive star explodes and dies. That's not the end of the story, of course, because that massive star may well have produced a black hole. That black hole may, 1 billion years later, come close to another star, and we may get this whole cycle of black hole jet formation. But if you look at the optical sky, you get something bright which fades away. We have realized in recent years that observations at millimeter wavelengths are very, very exciting for pretty much all of these phenomena. This is a really untapped area. There's been a lot of radio astronomy of astrophysical transients for quite a while, but we've realized that the same physical processes, which at relatively late times produce radio emission, at very early times produce very, very strong millimeter emission. So we'll have a dedicated program on the Africa Millimetre Telescope to look for transients. So gamma ray bursts are a particularly exciting target for the Africa Millimetre Telescope. Gamma ray bursts are something that happens sometimes when a massive star explodes. We don't know exactly why, but sometimes when a massive star explodes, a black hole, it seems, is very rapidly formed. A lot of the collapsing star falls onto the black hole, and extraordinarily powerful and fast jets are produced, which propagate out of the black hole. Here's a little animation of the kind of thing that we think happens when a GRB is formed. So a massive star is undergoing a supernova explosion. A black hole has formed at the center of the star. And again, it's the same thing. Black holes producing these jets. But in this case, the jets have punched their way out through the star. Sometimes they point straight at us and appear extraordinarily bright. And this is a phenomenon called gamma ray bursts. We made observations last year at relatively high radio wavelengths, but not millimeter frequencies, that showed unequivocally, I think, that if you had millimeter observations of these phenomena within perhaps half an hour of them being detected in space, then we would really discover or probe some very exciting new physics. And at the moment, no other millimeter telescope in the world has a program dedicated to this kind of astrophysics. So this will, as well as the EHT stuff, which is really the headline, I understand, this will really be a very exciting program for the AMT and for Namibia. And I will wrap up there. I want to thank you very much for your attention listening to me. As I said earlier, I'm absolutely delighted to be in Namibia, and I'm delighted to be part of this very exciting project. So to summarize, the most extreme astrophysics, possibly the most interesting astrophysics in our universe, is associated with black holes, astrophysical transients, and all the things that go along with them. There are huge ongoing programs, including Meerkat in South Africa, that are providing us with really incredible new data sets. And as an example, I'll remind you of that image of the galactic center with Meerkat. But the development of the AMT in Namibia will really allow us to take the next steps. This is not a regionally exciting thing. This is a globally exciting thing. The AMT in Namibia will dramatically improve the quality of the images the Event Horizon Telescope can make, and will really help us to improve our understanding of black holes. Thank you very much for listening.
Yes, thank you very much. Thank you very much, Rob, for this really great and inspiring talk. I have the guess, as a wild guess, that there might be still some questions left from the audience. So whoever wants to go first, just raise your hands.
Hi, good evening. Yeah, one question, actually two. One of it is these jets. You were mentioning they're moving with faster than the speed of light 5 times. They appear to be, sorry, I have to correct. They appear to be moving faster than 5 times the speed of light. Is that just an appearance then?
No, not at all. No, that's a great question. Yeah, it's an appearance. So there's a weird effect, and it's really not even particularly complicated maths, but it turns out that if something is moving close to the speed of light, at a relatively small angle, let's say to the line of sight to you, then it can appear to move faster than the speed of light. Okay, so if I have a jet moving like this, it can appear to move very, very fast. And the reason why is the following. We see it move some apparent distance over some period of time, but actually the time interval between seeing it at its start and finish is shorter than it should be, because it's been moving some distance towards you and shortening the distance. So the whole thing is a geometrical optical illusion. It's actually been known for quite a long time, but this is a really extreme example from within our own galaxy. Yeah.
Sorry, yes. And the other question is then, any observations now with a millimeter telescope or in the frequency range? Say, for instance, if Eta Carina explodes, it's 1,000 light years away. We will only see it 1,000 years later if it's tonight, even in millimeter or in microwave or wherever.
I mean, yes, but you wouldn't know it had exploded until you saw it explode. So in some sense, that distance doesn't really matter. So the first indication that Eta Carina had exploded, unless something very nasty was coming our way at the speed of light, which fingers crossed it won't, the first indication would be that you'd see it brighter in optical images. That's probably how it happened. The millimeter photons, and there certainly would be some, because this is a very powerful source and it's relatively nearby, they would arrive at the same time. So what we would do, as soon as we saw it getting brighter, we would immediately take the AMT, unless it was operating with the EHT at that moment, and we would swing round to look at Eta Carina. That would be a perfect definition of an astrophysical transient. Yeah. Yeah. Thank you.
Further questions? I see one there, the one there.
Good evening. What is the timeline on the AMT construction?
Yeah, That's a good question. So the PDR and CDR, the design reviews for the project will happen this year. It's a fairly ambitious timeline. So we were funded for 6 years from the ERC, the European Research Council, to produce this. And the idea would be that in the second half of the project, ideally, we'd be taking data. So 3 to 4 years from now, if everything works well, 3 to 4 years from now, we would hope to have first light. It's ambitious, but I must say, my experience, things have been being built faster and faster. Meerkat was built pretty rapidly. I know it's a different kind of thing. This particular telescope, we are probably going to use a relatively straightforward design, which has been used before. So we're optimistic we can do that. Yeah. Thank you. Other questions? Yeah, but they can't hear you online. Okay, yeah.
Okay, I have just one question. If I look at the baselines, especially from McMurdo, I see one glaring gap. Shouldn't there be also another project in Western Australia, maybe?
Yeah, I think, there clearly is a gap in the global coverage with the, which is essentially when the Pacific and Australia are pointing towards Sagittarius A star. Yes, I think if we had unlimited funds, we'd probably build considerably more telescopes. But right now, I'm more concerned with Africa than Australia. Yeah, yeah, yeah. Yeah, that's the long story to that statement as well. So, yeah.
Rob, thank you very much for a very, very interesting conversation there. Is there an easy way to explain how matter actually crosses the event horizon given time dilation?
Yeah, it's a tricky thing. So I think you're touching on the point that matter should sort of appear to freeze just as it, yeah. So what actually happens is that as the matter falls down towards the event horizon, it's moving towards a future where it will be inside the event horizon. So the event horizon itself is moving towards a future where it's slightly larger. Okay, so just as it gets to the point where it would have frozen, the event horizon itself has just moved out and basically stolen it. Okay, so it seems paradoxical, and it's a bit similar to the idea, when the massive star itself is collapsing to produce the black hole, it feels like it should freeze, but actually, from our point of view, from the distant observer, but actually what happens is the event horizon itself is moving outwards. There's some very interesting quasi-paradoxical things about that. It's an interesting thing, yeah. Anyone else? Yeah.
You said that all black holes have no charge at all, 0 charge.
I kind of said that. Do you have a follow-on question? Or you
yeah. Does that mean that there is no magnetic field around any black hole?
So that's a great question. On a macroscopic scale, which, as I sort of used the example of my dog earlier, basically anything larger than very, very, very small, the electric force is so strong, the electrostatic force is so strong that if you have anything that's charged, it tends to neutralize itself very, very quickly. And this would overcome, we cannot think of an astrophysical situation where you would end up with charged black holes, and we see no evidence for them. However, you touch on I think the more important point is, can there be magnetic fields around black holes? And we think that you need magnetic fields around black holes to launch these relativistic jets. But a non-charged black hole should not have a magnetic field, right? So actually what is happening is that the magnetic field must be supported in the matter which is falling down towards the black hole. So this flow, this rotating flow, we call it the accretion disk. And the accretion disk itself must support, at least in some phases, it must support a strong colloidal component we call sticking out of the disk component of magnetic field. And as that gets wrapped up, then some bits of the plasma, very, very fast, some bits of the plasma get thrown along field lines or something like that occurs. It's one of those things that it's impossible to write down a simple equation or 3 to describe it. But we see it emerging in very, in general relativistic simulations, you see things like these jets emerging. There's a kind of emergent property, but the magnetic field is sustained by the matter just outside the black hole, not the black hole itself. Yeah. Yeah. Okay.
You said that there are 3 numbers that describe one is spin, and you gave us one measurement, 0.9. Is that the only one observed? And if so, why is it 0.9? Why doesn't it vary or give us a range of what you've observed?
So, you know, towards the end of the talk, I focused on the fact that it would be a beautiful thing to be able to observe a black hole rotating. In the case of Sagittarius A star, because we've measured the mass very well, not just from EHD, but also from other observations. Andrea Ghez, you may have heard of, won Nobel Prize for basically very accurately measuring mass. If we can measure the rotation rate, given that we know the mass, we could measure the spin of Sagittarius A star. For many other black holes, there are estimates of the spin, but it's a very, very hard thing to do. Okay, so let me just give you a taster of what it's like. So it turns out that a non-rotating black hole, the event horizon, is twice as big as the event horizon of a very, very rapidly rotating black hole. So if you can measure how the size of the black hole, then you can perhaps estimate the spin. And the way to estimate the size is to see how hot the stuff goes as it falls down towards the black hole. And what you actually see is that stuff appears to get slightly hotter before it crosses the event horizon of a rapidly rotating black hole. Okay, so that's the tip of the iceberg of how complicated it is. And these are observations made from space, et cetera, et cetera. So the history of trying to measure the spins is the following, that it's very, very hard. Lots of teams have tried very, very earnestly to measure it. And yet it's still the case that for the same black hole, different teams report different spins. It's that hard. So that's where we're at the moment. There are lots of measurements, but it's hard for the community to converge on believing any of them. But actually seeing one rotate, of course, that would be a breakthrough. Yes.
This is from Francisco. Thanks for the great talk. During your presentation, you spoke about black holes on globular clusters. Can you explain how it could be formed and how difficult the angular resolution needed would be to observe it?
Thank you for your question online. Addressing the second point first, we will never have the angular resolution unless we find a very nearby stellar mass black hole to directly resolve the event horizons. But, you saw in the movie I showed that, you can see the jets propagating away from them. How do you form a black hole in a globular cluster? Well, the black hole itself would have formed at some point through the explosion of a massive star, like most of the other stellar mass black holes we believe that exist in our Milky Way and throughout the universe. The centers, and as far as we can tell, it resides at the center of the globular cluster. Now, globular clusters, as it sounds like are very, very dense environments. They have the highest stellar density probably anywhere in our galaxy, perhaps outside of the very center of our galaxy. And so what we see is there's a higher density of these kinds of objects in globular clusters. And the thinking behind this is that actually the stellar densities are so high that even if you had a singular black hole that drifted towards or into the center of something like a globular cluster, it would eventually get close enough to another star to capture it into a binary. And so the centers of globular clusters are like factories for producing these kinds of binary systems. Yep.
What happens to the stuff that fell into the black hole? Is it just like protons, neutrons very close together, or does it on the other side of the black hole turn into antimatter, or what?
We don't know, and this comes a bit back to the point I was making at the beginning, that we know that the physics that describes the event horizon, and we see the event horizons, we know that works, but we know the same physics tells us that it breaks at the center. So all I can tell you is that because event horizons appear to be real, then we can trust that maybe our physics just inside the event horizon is real, is a good description. And what we know there is that the matter crossing the event horizon, nothing spectacular will happen to it, but from the point it crosses the event horizon, it can never do anything but move towards the center. Okay? If you are just above the event horizon, you have a super powerful rocket, you can fire enough rockets to stop yourself moving any further. Once you cross the event horizon, those same rockets cannot save you. And in fact, you could fire a light ray. As you're falling towards the center, you could try and fire a light ray out, and the light ray will still go back towards the center as well. You're doomed at that point. What happens, we don't know, because these theories tell us that everything goes to a vanishingly small point. So we literally don't know what happens. Yeah.
So what force then is it really that pulls that matter on the other side of the event horizon. We learned that it is not magnetism. So gravity. But what is then gravity in this context? I mean, we do understand that's why we don't fall off on the Salbad. But what is gravity in the context of a black hole?
Yeah, that's a very good question. So the event horizon and the behavior of the matter outside the black hole is, it's the behavior of matter behaving as we expect it to behave under gravity. And our description of gravity in these regimes is general relativity, but it's gravity. It's the same gravity that keeps us on the Earth. Once the matter goes to center, as we say, I don't know what happens to it, and no one does, but it's clear that it still maintains its gravitational attraction. That's why the black hole continues to attract material into it, while the event horizon continues to exist around it. So I should rephrase my answer from earlier. It's true, I don't know what happens to it, but whatever it is, it retains its mass and gravitational attraction. But in what form it is, we have no idea. Yeah.
Yes, I would like to ask if, let's say, a mini black hole can be able to serve as a power plant, and if so, given that energy, how viable is it? Is it possible for humans to create a mini black hole to serve as a power plant on Earth?
Yeah, there's some interesting questions in there. So a long time ago, the famous scientist Roger Penrose, who also, like many other people in the story, won a Nobel Prize in the last few years for his work on black holes. He demonstrated a long time ago that it's possible to extract energy from a rotating black hole. Okay, so a possible future for the human race, if we can find a nearby black hole, is to actually extract energy from it. It's not we do things these days that they couldn't have dreamed of 200 years ago. Can we produce a black hole? I think we're not quite there yet. If we produced a very, very tiny black hole, then the amount of matter that black hole could accrete, we call this process of matter, adding on to the black hole, crossing it, would be absolutely tiny. So its rate of growth would be very, very small. So to give you, unless some very, very clever methods were envisaged. So there's a formula for the growth rate of the mass of black holes if you're feeding them continuously at the maximum possible rate. And it takes something like 30, I forget the exact number, it's something like 30 or 50 million years to increase the mass of a black hole by about a factor of 2, to basically double its mass. So I think that's, creating mini black holes in factories on Earth, no, I don't think that's a viable future. Yeah. But, extracting energy from a rotating astrophysical black hole, it's possible. They just get bigger. So one thing I didn't mention is that the size of a black hole is directly proportional, what we call linearly proportional to the mass of a black hole. So if you take the sun, you squeeze it down till it becomes a black hole, you get to, it's 3 kilometers basically. The sun, the same story I've been telling you, all the mass goes to a point, you end up with an event horizon 3 kilometers across. But if it was 2 suns, if it was a star twice the mass of our sun, that thing would be 6 kilometers across. Equally, though, if I took the sun and over some period of time made it into a black hole 3 kilometers across, over some period of time fed it another whole solar mass, it wouldn't be full, it would just grow to being 6 kilometers across. And this is the thing, again, to remember, it can't fill. All that matter goes down to a point at the center, and then the mystery starts again. Yeah. Yeah, over here, maybe, I don't know.
So yeah, if a black hole grows, why does it all still go down to a specific small point? Why doesn't it just stay at the specific small point if you add mass to it? So why does a black hole grow if you add mass to it, if everything goes down to infinitely small point?
So again, that's a very good question. So here's the point, that all the matter that crosses the event horizon goes to a point at the center, but you still add mass to it. Okay, you're still adding the mass to it. The stuff is still there. We just don't know. Again, to iterate, we don't know what's going on. All the stuff goes in, it's still there. We feel the gravity, but somehow all that new stuff we put in is still there in that infinitesimally small point in the center. I mean, I think all of this is just hammering home the fact that we don't know what happens at the center of a black hole. But we have established that it's a very important point to make, that, the gravity does remain. You add stuff to a black hole, it's strong. It's a stronger gravitational field. It's growing in its mass, but it's not as far as we can tell, this singularity at the center, we don't know what's going on. Sorry, where? Yeah.
Stars die. Do black holes die?
Well, some of you may have heard of something called Hawking radiation. And so a black hole left alone, not accreting, not growing in any way, in a perfect vacuum, will radiate away a very small amount of energy. And so if you take the stellar mass black holes that are produced by the death of a star, then the length of time required for one of those to what we call evaporate, to Hawking radiation, is much, much longer than the age of the universe, many, many hundreds of thousands of times. So those things will never have happened. However, I'm getting more speculative with time here. However, it is possible that in the very early universe, there were fluctuations in the density of the universe when it was in a very dramatic and chaotic state that produced smaller black holes. Okay, and it is possible that there were small black holes produced in the early universe that only now, at our epoch, 14 billion years later, are reaching the point where they finally evaporated to Hawking radiation. Because of course, when they release radiation, light energy is the same as mass. When they release radiation, they actually drop in mass a little bit. So there is a process by which it can happen. We've never seen any examples of it happening, and none of the black holes which you see in the universe, we'd never see it happen on any accessible timescale. Yeah. Yeah.
You said that as it dies, it loses mass to Hawking radiation and in turn loses size to Hawking radiation too. Does that mean that the surface area, the exposed area of the event horizon, also reduces, making it even longer? As in, like, as it dies, it also lives longer during its death.
You infer something good, but actually it's the other way around. Here's the weird thing. So as it emits radiation, it loses mass. As it loses mass, the event horizon shrinks. There's another property of Hawking radiation, which is the smaller the black hole, the hotter it appears to be, and in fact increases the rate at which you lose the radiation. So what actually happens to these black holes is that they slowly lose their mass for a long time, and the last few seconds they go whoop, and they go. And there would actually it's predictable how much energy would be released in this period of time, and there would be a flash in the sky, and it might look like some of the transients we see. It's just that so far to date, we've always found other explanations, and you need to be seeing them now. You need to invoke this idea that somehow in the very early universe, some exotic sort of medium-sized black holes were formed. But no, they don't last longer. They actually speed up right at the end. Yeah.
I was about to say one last question from Rio, who has his hand up for quite a while. Let's take the two of them. I think they're slowly filling up black holes. How are the information stored?
Yeah, I have a question. It's not my field, so it might be stupid, but as you explained how to measure the spin of a black hole, I'm thinking there are two things that are going on there. It's the angular momentum, the spin of the matter accreting into the black hole, and then there is of course the effect of that matter being caught in the ergosphere of the spinning black hole. I'm not sure, how do you distinguish between which is which? The angular momentum, the speed of the matter spiraling in, and some of that matter then crossing into the ergosphere that is actually, how do you distinguish between that? And is there a very big speed difference between, theoretically, between the matter crossing into the ergosphere, and then as it moves in there? I'm not certain how it works.
Yeah. Okay. So he's referring to the ergosphere. So there's a lot of information tonight. So this would be the last new bit of information. But when you have a rotating black hole, you have a region around it. You can imagine like a torus, a donut around the black hole, where the black hole's rotating, and anything, including light, that goes into that region is forced to rotate in the same direction as the black hole. It's extraordinary. You could have a black hole rotating like this, fire a light ray in like that, and the light ray would go turn around and rotate with the black hole once it enters the ergosphere. That's how strong the rotation of the black hole affects its surroundings. So your question is, how does the matter crossing it connect onto the speed of the rotating exosphere. And the reality is there are all sorts of different scenarios we see in astrophysics. So sometimes systems have been evolving or have been accreting. This is the process of matter falling into the black hole for a long, long time. And they've settled into a kind of steady state where they're almost matched. These speeds are almost matched. But we also know that there are phenomena where sometimes matter even appears to be moving on trajectories where it would be accreting in the opposite direction to the rotation of the black hole, and then actually has to do this kind of handbrake turn and turn around. So the whole range of possible sort of angles and speeds across this this boundary, we think we observe them in astrophysics. Yeah.
Right, as I said, last question.
My question was about how the spin of the black hole affects the size of its event horizon, because you made reference to that, so I'm not quite sure what the mechanics are behind that.
So the basic fact is the following, that if you have a non-rotating black hole, let's take the example of the sun. So if I take the sun and compress it down to become a black hole, then as I said a few times now, that produces a black hole 3 kilometers across in the case that it's not rotating. If I take this black hole and I grab it and I spin it so that it goes as fast as it possibly can, and in that case, that means that something which was rotating at the same speed of the black hole, just above the event horizon, would be moving at the speed of light. That's the maximal rotation. At that speed, the black hole, the event horizon would be only 1.5 kilometers across. Okay, so it shrinks by a factor of 2. And the way to, and this, of course, this comes from the equations of general relativity, but the way to think about this is that you may have seen these diagrams where, you know, falling into a gravitational potential is like going down a steeper and steeper slope. Okay. And you think about it like this, that, you know, the rotation of the black hole, so it's dragging this material really fast around it. This kind of supports it against falling down. Okay. There was this thing, I haven't seen it for years, but there used to be this thing where motorbike riders used to basically ride around the rims inside of cylinders. And it's only because they're going fast that they stop from falling down. Conceptually, it's a similar thing to that. The additional energy they get from the rotation of the black hole actually supports them against falling. It gives them enough energy to still potentially get back to our bit of the universe, which means that the event horizon is smaller.
Yes, I think that was a fantastic evening. Let's thank Rob Fender again with a big round of applause. And then with that, I want to hand the mic to our CEO of the Namibia Scientific Society, Ruth Malthio, to well, ask us out, to ask us to stay a little longer, and to ask us to come back.
Well, okay, you are allowed to stay a bit longer. Please do have a drink or two and pose the questions that you weren't able to pose now to him directly. I know not all questions on Zoom have been answered. May we give out your contact details so that they can ask you personally. I can tell you now already, this presentation will be available on YouTube within a couple of days, weeks, depending on availability, as well as the PowerPoint presentation. So if there's something that you didn't quite get or you want to review, you're welcome to do so on our YouTube channel. As you can see, we've got a couple of presentations coming up, a couple of tours. The next presentation being organized by the Bird Club on Thursday. But with that, I think it's time for a drink. Thank you very much and enjoy the rest of your evening.